Greetings, esteemed colleagues, Dr. Davidson and Omi. Our presentation today will be on the definition, applications, and uses of Benford's Law. Sit down, grab some popcorn, and enjoy our presentation.
Benford's law is the observation in many data collections of numbers. The leading significant digits are not uniformly distributed, but heavily skewed towards the smaller digits. At the end of the presentation, we will turn this magic to science. In 1880s, an astronomer named Simon Newcomb looked at many logarithm books, what there was instead of calculators, and found that the first few pages were worn out more than the rest. He then realized that in the logarithm books, the numbers that started with the digit 1 were much more common and used more often than all the other leading digits. Only about 6 decades later, in the late 30s, did a physicist by the name Frank Benford credited Newcomb's work and turned it into Newcomb-Benford's law, or Benford's law.
Let's start with mathematically. What does Benford's Law look like? It is defined as P subscript B at D is equal to the log 10 base 10 of 1 plus 1 over D, where D is a leading digit of a data set and B for Benford. One of the main reasons Benford's law works is shows the probability of a leading digit in a range of values. This graph shows how the probability of the leading digit being 1 over a certain range of values. The first peak is at 100%, while the following peaks afterwards are all around 30.1%, which will be explained later on in our presentation. These two graphs shown are the two different styles for showing Benford's law visually. Both of these graphs depict pure Benford's law scenarios perfectly following the distribution mean, meaning they have large numeric data sets, no real or artificial restrictions, and the magnitudes of orders of the data sets are evenly spread. The following graphs below mainly are depicted as a probability distribution due to them just being much easier to read/follow.
We tested Benford's law using Stirling's approximation. Using the actual factorial on the left-hand side and Stirling's approximation, the right-hand side, we created separate distributions to see if they converged to Benford's law. When we look at the values as n approaches 171, which is the greatest value we were able to compute, we see that both graphs are identical and follow Benford's law.
Benford's law works for datasets only with numeric data, and the datasets follow the law much better when the datasets are very large. Benford's law is more accurate for certain datasets that span many orders of magnitude. The more orders of magnitude the data evenly spreads, the more Benford's law applies. More simply put, Benford's law will only apply when the dataset covers magnitudes with leading digits from 1 to 9. The numbers in the dataset to follow Benford's law must be created naturally without being assigned.
The following slides will depict examples of Benford's law being used with real-world examples. Benford's law is more accurate for certain data sets that span many orders of magnitudes. For example, if we look at the variety of cases for the novel coronavirus COVID-19 that spans over 218 countries, we see that even with the same number of data sets, the higher the value in the data, the closer the graph follows Benford's law. You can see that the population graph follows Benford's law much more than the previous graphs. Moreover, when the sum of all plots have been stated into a single plot, you can see that with a higher set of data, we get even closer to Benford's law. That's right, physics constants too. Some arithmetic series too.
All right, counterexample of Benford's law. First up, we have small sample sizes, lower than approximately 100 numeric entries, won't have enough data points to accurately follow Benford's law. Up next, we have a random number generator, will produce numbers where the distribution of leading digits will appear uniformly, each with a probability of around 11.1%. Or perhaps the winning lottery tickets for major weekly lotteries will always be random and constrained to the number of tickets sold each time, so again will not follow Benford's law. Lastly, is when data sets are tampered with, meaning someone went through a data set and changed some of the numbers to whatever they please. Whatever numbers they pick for the data set, when compiled, of all the leading digits, the leading digits will no longer follow Benford's law.
In the article, How Do Numbers Begin? Torres et al. Stated that prime numbers follow Benford's law. We were pretty surprised and wanted to see it for ourselves, so we plotted it and found that prime numbers, in fact, do not follow the law. A set of truly random numbers do not give rise to Benford's curve. This can be explained using Shannon's entropy. The maximum disorder of randomness is when each state or digit has the same probability of occurring, so everything is just as surprising.
Going back to the example of COVID, there was some concern as to whether China's case numbers were manipulated. Researchers investigated the daily number of confirmed cases during the exponential growth period of the virus in China, Italy, and the US. There may be some concern as to whether or not those that did not get tested at all would have affected the data, but as it stands, China's cases do follow a Benford distribution. Benford's law has also been used considerably in the past to bring attention to election fraud. There are, however, many other factors that can affect votes to prevent them from following a Benford-like distribution. A common inconsistency is that the population of different counties and towns may be too small to follow Benford's law. So it is found, though, that using the second digit, Benford's law, is a more accurate test of whether something is wrong. In any case, though, Benford's law does not serve as proof of fraud. It is a mere tool to raise awareness if something is fishy. And Benford's law is also used similarly with financial fraud. It may bring awareness to cases that need further investigation, but it cannot actually prove fraud. Jen Goldbeck, a computer scientist, analyzed various social platforms and found that the amount of friends or followers individuals had follows Benford's law. Dr. Goldbeck continued the analysis and found that accounts that do not follow Benford's law were bot accounts, and they were following accounts of the same type. If we look at a matrix representing an authentic image or video or audio file, the numbers contained in that matrix will follow Benford's law. Every time an image is copied or modified, it gets compressed. This compression changes the numbers contained in the matrix such that it no longer follows a Benford distribution. The distribution of numbers gradually gets more uniform as the file is further compressed, which maximizes the Shannon entropy. This increase in entropy corresponds to a decrease in the information stored in the file, showing up as a decrease in quality, which is the purpose of compression in the end.
To derive Benford's law, we can consider a real number, a to the power of r. Suppose we have a random variable r that is uniform along the logarithmic interval, where p is any integer. The leading digit d is then in between this interval, and this becomes clear when we see the interval for a to the power of r. Here, 10 to the power of p represents the digit placeholder, and the leading digit only depends on what value d is. Now, since the interval is uniform, the probability of digit d is then the length of the interval containing d over the entire interval. That is, the probability becomes this expression. Following the same logic, we can find the distribution for the second digit. The probability of finding d is in the total length of all intervals that d falls under. The probability is then this expression, where k is the leading digit, and in general, Benford law then becomes this expression. Another property that Benford's law follows is base invariance. Any number system will follow Benford's law. For instance, take base 3. The digits here are then 0, 1, 2, and 3. And so the probability for the leading digit becomes this expression. Additionally, another surprising result that arises from Benford's law is scale invariance. That is, when we multiply the result by some scalar c, it will also follow Benford's law. An instance of this is when changing the units of the data from, say, kilometers to feet. The data will still follow Benford's law. This can be seen by considering adding the scalar c to the random variable r. Then the interval will shift by c units. The interval of the leading digit, d, falls under, will also become shifted by c units. And the probability then just becomes the same probability we would expect, which is Benford's law. An attempt to explain why many real datasets follow Benford's law is to examine the multiplicative central limit theorem. Recall at the beginning that when independent random numbers are multiplied together, they will begin to follow Benford's law. And what the multiplicative central limit theorem states is that when multiplying n independent random variables, and as n approaches infinity, the distribution becomes a log normal distribution. This creates a uniform log distribution that follows Benford's law. Now, if we were to consider real-life data, there are many, many independent factors that are multiplied together. Take one of Benford's examples, the length of rivers. Examining the distribution of the lengths of rivers in the New York State, it follows a log normal distribution, and as expected, it also follows Benford's law. But why do rivers have that length? Well, it can be the product average rainfall, hot periods, and even sunspots, just to name a few. By this, we have many independent random variables being multiplied together. And that's a reason why river length will follow Benford's law. So, to summarize, Benford's law is defined as the probability of the leading digit is equal to log base 10 of 1 plus 1 over the leading digit d. Benford's law was initially discovered by Simon Newcomb in the 1880s and was later redefined by Frank Benford in the 1930s. Many real-world examples of Benford's law include physical constants, COVID-19 cases, and the Fibonacci sequence. The applications of Benford's law can prove certain datasets have been manipulated, and the most effective way to view Benford's law data is on a probability distribution graph.